Problem number 5 asks us to find the temperature of a hot rock after it is dropped into a large body of cooler water at different times. And this one seems pretty tricky at first. It involves Newton's law of cooling, which is over here to the right. However, if we kind of step through this problem slowly, use some calculus to find the temperature profile of the rock, then we can solve for the temperature of the rock at any given time throughout this process. In order to find the temperature profile of the rock, we need to get our small t, which is defined as time in this equation, on one side of the equation, and our large T, which is the temperature of the rock at any given time, on the other side of the equation. And if we have these two on opposite sides of the equation and no unknowns, then we will have a temperature profile of the rock. So if we start by looking at the equation that we were given for Newton's law of cooling, let's plug in what we know and then move some things around and try to get that, time on one side and temperature on the other side of the equation. So to start, just rewriting what we were given, we're told that the change in temperature over the change in time is equal to our K times our initial temperature, which we know is 20, minus our temperature of the rock at a given time. Now we want to isolate that big T, as that is the temperature of the rock at a given time, and solve for it in terms of time so that we can find the temperature of the rock given a certain time. And so to do that, let's move that term to the other side of the equation and then bring our dt over here. So we've got big dt over 20 minus t is equal to k dt. In an effort to try to get rid of these dt's, we can take the integral of both sides. And so on the left-hand side, we'll be left with the integral of 1 over 20 minus t dt. And on the right-hand side, we're left with the integral of k dt. Taking these integrals, on the left-hand side, we're going to have the natural log of 20 minus t. And on the right-hand side, we're going to have kt plus c. To get rid of that natural log, we can raise both sides to e. And so we're left with e to the ln of 20 minus t is equal to e to the kt plus c, because we know e to the ln just cancels out. Canceling it out, we're left with 20 minus t is equal to e to the kt multiplied by e to the c, knowing our exponent rules and kind of distributing that out on the right-hand side. Now that we have an equation with our temperature on one side and our time on the other side, let's try to plug in some of our initial conditions in order to get rid of some unknowns. So we know that at time 0, our rock is equal to 100 degrees Celsius. And so we can use that information to try to get rid of some of these unknowns. And so let's plug that in. We're going to have 20 minus 100 is equal to e to the k times 0 multiplied by e to the c. And so we're left with negative 80 is equal to 1 times e to the c. And so that tells us that that e to the c term is just equal to negative 80. And so we can rewrite that equation as t is equal to 20 plus 80 times e to the k t. Now we almost have our temperature profile of our rock. We're just missing that k term. However, thankfully, we have another initial condition. We know that at time equals 1, our rock is 90 degrees Celsius. And so we can plug that information in and solve for our K. And so we've got that 90 is equal to 20 plus 80 e to the k times 1. And doing some rearranging, we get that 70 is equal to 80 e to the k. And moving some more things around, we find that e to the k is equal to 7/8. And so instead of solving for k, we can just take that entire term and plug that into our temperature profile. And so we're left with our temperature profile to the rock is equal to our temperature of the rock at any given time is equal to 20 plus 80 times 7/8 raised to the time. Finally, using this temperature profile, we can solve for part A, which asks us to find the temperature of the rock at T equals 5. So if we just plug 5 into that equation, we know that T is equal to 20 plus 80 times 7/8 raised to the 5th, and that will equal T is equal to 61.03 degrees Celsius. And so that's how you do part A of this problem. Part B asks us to find at what time the rock will reach 50 degrees Celsius. And so this is pretty easy. Now that we already have the temperature profile of the rock, we can just plug in 50 for our temperature and solve for time. So let's do that here. We've got 50 is equal to 20 plus 80 times 7/8 to the time. And so doing some math, moving some things around, we're left with 3/8 is equal to 7/8 to the time. Next, to isolate T, we can take the natural log of both sides. And then we can bring our T down to the front. So we're left with ln 3/8 is equal to T times ln of 7/8. Let's move this term over to the left-hand side and solve for T. We're going to get ln of 3/8 divided by the natural log of 7/8 is equal to our time T. And if we do that math out, we find that our time T is equal to about 7.35 minutes. And that's how you do part B of this problem. So overall, this problem is pretty tricky, but the key thing is just finding that temperature profile and using that calculus and kind of rearranging some things to find that temperature profile. Once you have the temperature profile, which relates the temperature of the rock to the time, then finding the rest of the answers is pretty simple. So I hope this walkthrough helped.